Today we're doing our work in Chapter 4, and we'll be looking at another application of derivatives, which would be L'Hopital's rule, which allows us to take limits. All right, we've seen that being able to evaluate limits is a very important part of what we've done in building up to these derivatives. So L'Hopital's rule does allow us to a technique for evaluating limits of quotients. So specifically when we have a function over another function, we're going to look to see when we can use L'Hopital's rule and how it applies. Okay, just to briefly review a few of these limits here. If we're looking at the function y equals x, which is just this diagonal line here, if we look at the limit as x approaches 0, that means as we're coming in toward 0 from both directions, and you can see that means following this and following this. So it's coming to a y value of 0, and that's where we get the 0 as the limit there. If we're going to, as x goes to infinity, that means we're following it up this direction. So we're continuing to go higher and higher, going to infinity. Kind of by the same token, if we're going in the negative direction down this way, we're going down here to negative infinity. If we look at the function y equals x squared, which is just a basic parabola, if we're looking at the limit as we approach 0, that is taking us, if we follow it in from both sides, it's taking us down here to the origin, and that's where we get 0. Because remember, your limit values are the y coordinates as the x does whatever this is describing. So as x gets closer to 0, the y is getting closer to 0. Okay, as x goes to infinity, that means we're following it up here, and that's taking us to positive infinity. As x goes to negative infinity, which means moving in this direction, we're going to follow it, and it's actually also going to go to positive infinity. This is a reciprocal function, 1 over x, so you can see the graph of it here. And remember, graphing is one of our techniques for finding limits. So if I'm looking at this, this would be the limit as we approach, as x approaches 0 from the positive side. So that's going to be this part here. So that's actually taking us off the top of the graph, which is taking us to infinity. If we're approaching 0 from the left side, that's going to take us in from this direction, which means that we're approaching negative infinity. And because they're going to two different values, so because these two don't equal each other, we're going to have to say that the overall limit does not exist. So these are things we talked about back in Chapter 2. It's been a little while, so we just wanted to review a couple things here. Okay, if we look at the limit as x goes to positive infinity, that means this time we are following the graph going in this direction as we go toward infinity on our x's. If you can notice, the y is getting closer and closer to this x-axis. So as the y values of these points along this graph are getting closer and closer to a y value of 0. We do the same thing from the other side. This time again, we're going toward negative infinity. Okay, so that's taking us back here. And the y values for all of these points on this curve are getting closer and closer to that x-axis, which is 0. If we look at the 1 over x squared function, then and look at the limit as we approach from the right side, that means we're following it in this way, and so that's taking us up here to positive infinity. If we approach from the left side, that's following it in this way. We're again going to positive infinity. So the overall limit, if we're going to describe the limit itself, it is going to infinity. So technically it's a does not exist because we can't actually get to infinity. Okay, if we go as the limit as x goes to positive infinity, well, positive infinity for the x's is out here. So if we're following it going this way, the y coordinates of all these little points are getting closer and closer to 0. And if we follow it in the other direction, going to an x value of negative infinity, that means we're going to follow it along here. So all these little points, the y coordinates are getting closer closer and closer to 0 as well. If we look at the exponential function, you can see the graph of the exponential function here. So the limit as x approaches 0, that means coming in from both sides, we're actually approaching this point here, which is 1. So that's our limit for that value. As x goes to negative infinity, that's following it going this way. We can see that it levels off, that this is actually a horizontal asymptote, and it's getting closer and closer to that. So the y values there are getting closer and closer to 0. And if we follow it going in the positive infinity direction for our x's, that's going to take us here, and we're going to follow it off the chart off the top of the graph to infinity. If we look at the graph of y equals e to the negative x, you can see that down here on the right. Okay, as we approach 0, coming in from both directions here, our y coordinate is 1, and so our limit would be 1. If we go to negative infinity, going back this direction, that means I'm going to follow the curve in this direction, so I'm going to positive infinity for that limit. If I'm going to positive infinity, that means I'm following it going in this direction. And so the y coordinates for all these little points are getting closer and closer to 0. All right, the natural log of x, you can see the graph for that. So if we look at the limit of these, the natural log is not defined for negative numbers or 0, so that's why we don't have a graph over here. We can only follow this in from the right side. So approaching 0 from the right side takes us down and down, so we go to negative infinity. If we're approaching infinity, going toward infinity, we're following our graph going in this direction, and so it's not rising quickly, but it is rising, so there is no like top or highest value. It just continues to get higher and higher, and so that's why it goes to infinity. Okay, we can kind of take the things we just looked at and generalize some of these things. So if I know that the limit as x goes to infinity, let me back up to that. Okay, so the limit as e to the x, the limit of e to the x as x goes to infinity is infinity, okay? So it's going like this. So if I look at the problem we were just talking about here, we know that e to the x is going to go to infinity. So multiplying it by 3, or even throwing another number in here, is not going to keep it from going to infinity. If anything, it's going to cause it to go to infinity faster. We don't really judge how fast it goes. We just need to know where it's going. So it's going to infinity, and these values here are just increasing the speed of how fast that occurs. Okay, on this one was the e to the negative x one, and we're looking at it as x goes to infinity. So let's look back again at the e to the negative x. So as x goes to infinity, we see that this is actually going to 0. So we want to keep that in mind as we apply that to this example here. So this part here, as x goes to infinity, is going to be going to 0. Okay. So if it's going to 0, multiplying it by 5 is still going to cause it to go to 0. So these constants here don't have a lot of effect on when you're going to infinity in these cases. Okay, this one, all this does when we put this plus 4 in here is it shifts it to the left 4 units. So it doesn't really change where it's going. Again, it might get there a little faster or a little slower, but it's not going to change it. So looking here, if we look at the limit as x goes to infinity of the natural log of x, it's going to infinity. So if I shift this to the left 4 units, which is what our problem called for, it's still going to go to infinity. It's not going to cause it to not go to infinity. And the same thing here, if we're approaching 3 from the positive side, let's look back at this example here. Okay, so if we're approaching 3 from the positive side, this the one we were looking at had been shifted. Okay, so if everything shifted to the right 3 units, our graph is going to look more like this. Okay, so as we approach 3 from the positive side, that's going to take us down here, and we're going to be going to negative infinity. Okay, here are a couple you could practice on just to make sure you understand this. Okay, this one, if we're looking at it, basically you think about if I were to put in a really large number in the negative direction, so like negative a million or something like that, this negative and this negative are going to cancel each other out. And so basically I'm going to have like 2e to the positive 6x. And so because of that, that means that this is going to be going to infinity as its limit. This one, if I put a negative infinity in, I'm going to have like 3e to the negative 2 million. So this is going to be going to 0 because the e is going to have a negative exponent. Okay, this one we would be moving to the left 4 units. So our normal natural log graph is going to look something like this. So if we move it to the left 4 units, it's going to look, and this is not a great drawing, but it's going to look something like this. The main thing is that on our original graph, we would have had a vertical asymptote at 0, and that vertical asymptote gets shifted 4 units to the left as well, so it looks something like this. So if we want the limit as x approaches negative 4 from the positive side or from the right side, that means we're going to be following it down this direction. And so it's going to be going to negative infinity. This is going to shift our graph to the right 10 units. So where it normally would have been this original graph here, we're going to move everything to the right 10 units. So we're going to be out here at 10 and 11. And we want to know what's happening as x goes to infinity, which means as x is going this direction, so it's going to be going to infinity. Okay, so that was kind of a review of limits. Let's take a look at how L'Hopital's rule plays into this. So L'Hopital's rule allows us to deal with these indeterminate forms that we talked about before. So some indeterminate forms can be handled pretty easily, and then others may not. So just to review, the first thing you've got to do is you need to see if you are dealing with an indeterminate form, which in most cases means plug the 3 in and see if you get like 0 over 0. So if I get 3 squared minus 9 over 3 minus 3 is going to give me 0 over 0. So prior to L'Hopital's rule, what we would have done is we would have taken this same limit as x goes to 3, but since this factors, I would do minus 3 and plus 3. These will cancel. And then the limit as x goes to 3 would be 3 plus 3 or 6. So that's not hard to do, but L'Hopital's rule will give us another way to approach these. Okay, so we're going to be focusing on these indeterminate forms, the 0 over 0, when we have a quotient that's being divided, with like two functions being divided. Okay, so what L'Hopital's rule says is that for these indeterminate forms, if the limit of the original function is 0 and the limit of the denominator or the numerator and then the limit of the denominator is also 0, then the limit of their ratio is equal to the limit of the ratio of their derivatives. Okay, so this limit would be equal to this limit. So there's times when this limit may be indeterminate, but this limit actually exists, and therefore if this limit exists, then it can help you to figure out what the original limit was. And it also holds whether it's going to C, or it could be a one-sided limit, or it could even be going to infinity or negative infinity. Okay, so let's look at this. First thing is to see if it's in indeterminate form. Okay, so if I go and I plug 2 in, I'm going to have e to the second minus e to the second over 2 minus 2. So that is definitely 0 over 0. So it is an indeterminate form, which means L'Hopital's rule would exist. So L'Hopital's rule tells me that the limit as x goes to 2 of this function that I've been given here is equal to the limit as x goes to 2 of the derivative of each of these. Now we don't apply the quotient rule. We just take this as one function and we take this as another function. So if I'm looking at this numerator and taking the derivative of that, the derivative of e to the x we know is just simply e to the x. E to the second is a constant, so its derivative is actually 0. So the derivative of that numerator is e to the x. Here, the derivative of x is just 1, and the derivative of 2 is 0. So I end up with this that I've got to simplify, which is when I plug the 2 in, going to give me e to the second. And so that's the value of my original limit, okay, by L'Hopital's rule. Okay, so let's try another one here. The limit as x goes to 1 of the natural log of x over x. So on this one, if I plug 1 in, I'm going to get the natural log of 1 over 1. The natural log of 1 is 0. Okay, so L'Hopital's rule does not apply. But 0 over 1 is just simply 0. And so that's going to be my limit. So don't think that every problem is going to be solved using L'Hopital's rule. Not every problem is a case where L'Hopital's rule will apply. So like this one was actually just a direct substitution and you come up with your answer. And you can see that if you actually did apply L'Hopital's rule, what would happen is you would get an incorrect answer. So if you apply L'Hopital's rule if you use L'Hopital's rule when it actually doesn't apply, it can give you an incorrect result. Okay, so here's one for us to try. If I'm evaluating this limit here just by direct substitution, I'm going to have e 2 times 0 is 0 minus 1 minus 2 times 0. So anything to the 0 power is 1. So I'm going to end up with 0 in the numerator. And then 0 squared obviously is just 0. So I do have 0 over 0, so that tells me that it does apply. And I just need to take the derivative of that. So the limit as x goes to 0, the derivative of this is going to be e to the 2x times 2. Don't forget the chain rule part of that, because that would be e to the 2x times the derivative of that 2x, which is 2. The derivative of 1 is 0, so I don't have to put anything there. And the derivative of negative 2x would just be minus 2. And then the derivative of x squared would be 2x. Okay, so if we evaluate this, what I'm going to have is I'll have e to the 0 times 2 minus 2 over 2 times 0. Okay, so this is going to be 1 times 2 will be 2 minus 2 over 0. Okay, so if I look at this, what happens is I still have another indeterminate form. Okay, so I can actually go again with this. I can keep using L'Hopital's rule until it either no longer applies or I come up with an answer. Okay, so if I'm going to take the derivative again of this, then the derivative of and I'm going to rewrite it first before I start taking derivatives. I think it would be easier. Okay, so if I'm going to take the derivative here so I can apply L'Hopital's rule, this is going to be 2 times the derivative of e to the 2x, which would be e to the 2x times 2 because I have to use that chain rule for this part, this exponent part here. The derivative of 2 is 0. The derivative of 2x would be 2. Okay, so these 2's actually will cancel out. And if I plug 0 in here, I'm going to have 2 times e to the 0, which is 1. So I'm going to end up with 2 as the value of my limit. So in this case, I had to apply L'Hopital's rule twice before I got an answer. Okay, here's one for you to try. Always start out by checking to make sure that it would apply. So this will be e to the 4th minus e to the 4th over 4 minus 4. So that is 0 over 0. So it would apply. So using L'Hopital's rule, if I take the derivative of this numerator, it would just be e to the x. Because this would be, the derivative of this would be 0. And here the derivative would be 1. So I'm going to end up with e to the 4th. Okay, if we look at this one, first of all, we're going to evaluate it here. So we'll have the limit of 1 over 1 minus 1 to the 3rd. Okay, the limit, or this not limit, the natural log, sorry. The natural log of 1 is 0. And then that's going to be 0. So that does tell us that we can use L'Hopital's rule. So L'Hopital's rule tells me that my original limit is equivalent to the limit of the two derivatives. So the derivative of natural log of x is 1 over x. The derivative of this, we're going to have to use the chain rule. So we're going to bring the 3 down, recopy that parenthesis, decrease our power by 1, and then multiply it by the derivative of this inside, which turns out to just be 1. Okay, so now we're going to evaluate here. So we're going to have 1 over 0, 1 over 1. And then here we're going to have 3 times 1 minus 1 squared times 1. So we're going to end up with 1 over 0, which basically gives us an inconclusive limit with that, which means we would need to use other techniques for finding the limit of this one. Graphing could be one of the techniques that we would use. So if you looked at the graph of this, what you'll see is that there's actually a vertical asymptote at 1, and it's going to infinity. So because of that, we end up with the limit equaling infinity. Okay, this is a rough sketch of what you would see on the calculator. So here's that vertical asymptote at 1. And as we approach from either side, from the right and from the left, you can see they're both going to infinity. Okay, we can try this one. If I plug 0 in, I'm going to have 0 over, plug 0 in here, I'm going to have 1. 0 over 1 is just 0. It's not an indeterminate form, and so that I would not need to use L'Hopital's rule on that one. Look at this one. Here we are looking at the limit as x goes to negative infinity. So looking at this, we'll have the natural log of 1 plus, if I'm putting negative infinity in here, that would be e to the negative infinity. So that means this is going to be going to 0. And 2 times 0 is just going to be 0. And if I put negative infinity here, then it's going to be going to 0. The natural log of 1 is 0, so I am working with a 0 over 0 indeterminate form and can apply L'Hopital's rule. So the limit as x goes to negative infinity, we're going to take the derivative of this. So that's going to be 1 over 1 plus 2e to the x times the derivative of this. The derivative of 1 is 0. The derivative of this is going to be 2e to the x. And then the derivative here would be just e to the x. So I have 2e to the x over 1 plus 2e to the x over e to the x. and that we've still got to take the limit as x goes to negative infinity. So we need to make sure we keep recopying that each time. Okay, I'm going to clean this up a little bit. So I have 2e to the x over 1 plus 2e to the x. And then I'm going to multiply this by 1 over e to the x. And what that's going to let me do is I'm going to cancel these e to the x off. Okay, so all this is equivalent to the limit as x goes to negative infinity of 1 over 1 plus 2e to the x. Okay, as x goes to negative infinity, that means this would be e to the negative infinity, and basically that is going to 0. 2 times 0 is 0, so I end up with 1 over 1, which is just going to be 1. Except I dropped a 2 here that I do need to continue to bring down, so it is going to be, instead of 1, it's going to be the 2. Okay, if we're looking at this one, what we're going to have, if I start out to see if I'm able to use L'Hopital's rule, if I put infinity in, the natural log of infinity is just infinity. So I'm going to have infinity over infinity. So this does tell me that I can use L'Hopital's rule with this. So the derivative of natural log of x would be 1 over x. The derivative of just x is 1. So that comes down to the limit as x goes to infinity of 1 over x. So if that would be 1 over an extremely large number. So this is going to be equal. Okay, so the limit as x goes to either infinity or negative infinity can give us these horizontal asymptotes that this is talking about. So when it's saying find all horizontal asymptotes, that's basically wanting you to take the limit from both directions with that. So let's take a look at this problem here. We want to consider the limit as x goes to negative infinity. So when we do that, we're going to end up, if I'm putting negative infinity into x squared, I'm just going to end up with x. Actually not x, I'm going to end up with infinity, because even though it's a negative that I'm putting in because I square it, it gets rid of the negative, I'm left with the positive. Okay. And then the denominator is the e to the x. So if I'm plugging in negative infinity here for this, I'm going to get 0 for it. Okay, so what that shows is we can't apply L'Hopital's rule in this situation because it's not 0 over 0 or infinity over infinity. So one method we can look at here is to actually rewrite this. We could rewrite it as x squared times e to the negative x. So if I'm looking at the limit as x goes to negative infinity of x squared e to the negative x, if I'm putting in negative infinity in here, the two negatives will cancel out. And so this is going to be positive infinity. So infinity times infinity is still just going to be infinity. And basically, if we look at the limit as x goes to positive infinity, which would be the other part of finding the horizontal asymptotes, when I plug in infinity here, I'm going to get infinity over infinity. So that is a case where L'Hopital's rule applies. So the one we just finished was infinity over 0. So we can't use L'Hopital's rule for that, but we can use it here for infinity over infinity. So I'm going to take the limit as x goes to infinity of the derivative here, so that would be 2x. The derivative here would be e to the x. Okay, so that's going to be in 2 times infinity is still infinity, and then e to the x is going to be another infinity. So that means we've still got an indeterminate form, so we can keep going with this, keep taking derivatives. So the derivative of 2x would be 2. the derivative of e to the x would just be e to the x. So we end up with 2 over infinity. And so 2 over infinity is actually going to just be 0, because 2 divided by a really large number is a really small number. Okay, here are a few to practice on. This one, number 2, is actually a duplicate, so there's really no reason to go back through that one. If we look at the first one here, if we plug in and see if L'Hopital's rule applies, we'll have e to the 0 minus 1 over 0. So we'll have 0 over 0. So yes, it would apply. And then when we go and we plug in, or we take our derivatives, the derivative of e to the x would be e to the x. The derivative of 1 is 0. The derivative of x is 1. So we end up with e to the 0, which would be 1. We said we've already done this one, so we're not going to do it a second time. This one, if I'm evaluating here, I'm going to have 1 minus 1 would be 0 over 0. So yes, it would apply. So we'll look at the limit as x goes to 1 of the derivatives here. So that would be 2x over 1. So we end up with 2. When we plug 1 back into that, we end up with 2 as our derivative. And then on this one, if we plug 0 in, we're going to have the natural log of 1 over 0. So yes, we can apply L'Hopital's rule, and so that means it'll be the limit as x goes to 0 of the derivative of each one of these. So the derivative of this natural log x plus 1 would be 1 over x plus 1. The derivative of x would be 1. Okay, so if I put 0 in here, I'm just going to have 1 over 1, and then all that's over 1, so we end up with 1 as our answer.